Hello and welcome to the last installment of Boring White Guy Talks Numbers. In this session we will finish up the class talking about calculus in polar coordinates. So we're going to just state some formulas for area and arc length in polar coordinates without deriving them. We didn't talk enough about polar coordinates to really get our hands dirty with the derivations, but we talked enough to do these problems. So the area of a polar region. If we wanted to find the area beneath the curve, how would we go about doing that? The area A between rays theta equals A and theta equals B, and the equation r equals f of theta is given by A equals the integral from A to B of 1/2 f of theta, quantity squared, d theta. So let's do an example of this. Find the area enclosed by the rows r equals sine of 3 theta with graph below. So we have the graph is you start at the origin and then you go up here, draw a rose petal, draw a rose petal, draw a rose petal, and then repeat. And my last rose petal looks horrible. Let's try that one more time, but faster. Wee. Yeah, that looks better. And moreover, I'll give you these 2 points, these 2 rays. Oops. We have theta equals 0 and theta equals pi over 3. The first petal is sandwiched between these 2 rays. Okay, solution. So we're interested in the area of the first rose petal. So first off, we have f of theta is r, is sine of 3 theta. We want the area of the whole rows, the area inside of the whole rows. But we notice that this rose has 3 identical petals. So we find the area of one petal and then triple it. Which is why I only gave us the information for the first petal. So we have the area is the integral from A to B. In this case, I gave us the rays 0 and pi over 3. So 0 to pi over 3 of 1/2 f of theta squared. So that is sine squared of 3 theta d theta. Well, this area, this integral is a trigonometric integral. We have powers of sines and cosines. Since all of the powers are even, we have sine squared and cosine to the 0. We're going to use the half angle formula. So this is pull out the 1/2 integral from 0 to pi over 3 of 1 minus cosine of 6 theta divided by 2 d theta. Well, this is 1/4 integral from 0 to pi over 3 of 1 minus cosine of 6 theta d theta. This is 1/4 times theta minus sine of 6 theta divided by 6, evaluated from 0 to pi over 3. So this is 1/4 times, evaluate this at pi over 3, we get pi over 3, minus sine of 6 pi over 3 is sine of 2 pi, divided by 6, minus evaluating at 0, so that would be 0. Distribute the negative sign to get plus sine of 0 over 6. And sine of 2 pi is 0. Sine of 0 is 0. So we just get pi over 12. This is the area of one rose petal. So the total area is A equals 3 times pi over 12, which is pi over 4. Similar to Cartesian coordinate systems, if you want to find the area between two curves, you just find the area of one and subtract the area of the outer region, and then subtract off the area of the inner region that you want the area to be between. And we'll do that this same way here, just a little bit different because our rays are always starting at the origin. So you'll actually see that the example we're about to do would be very hard to do in Cartesian coordinates, but it's going to be a little bit simpler in polar coordinates. So example, find the area of the region outside the cardioid, given by r equals 1 minus cosine theta, and we want the area to be inside the circle that intersects the cardioid at the given point. Okay, so what does this look like? I have to give you a picture because I said at the given point. So we have the cardioid. It's going to look something like this. And then we have the circle. It's going to look something like this. Let's see if it fills it in nicely. Yeah, that works. So we want this area. And notice this would be very difficult in Cartesian coordinates, just because if you draw your lines going up to see what the radii would be, you would have to break it up into like 4 different integrals. You have this integral that has outer region, the circle, and then inner region, the cardioid. Then you come over here and you have this region that would have just the area beneath the curve of the cardioid. And then you have this region that is just the area beneath the curve of the circle. I guess 3 regions, not 4. But still, rather complicated. And also, we would need this point here, and I have no clue how to find that easily. So I'm supposed to give you 2 points. So we have the circle intersects the cardioid at 2 points. The top point is 3/2, comma, 2 pi over 3. And the bottom point is 3/2, comma, negative 2 pi over 3. So So this wasn't drawn perfectly because these are supposed to be in a straight line, but good enough. Okay, solution. How would we do this? So we do this the same way as in Cartesian coordinates. We're going to subtract the two areas. So we can find the area of the cardioid because we were given the formula. It's r equals 1 minus cosine theta. We were not given the equation for the circle, which we will need to find the area of the circle. So we're going to have to figure that out. And notice that I gave you the coordinates in polar coordinates. So this is r equals 3/2 and theta equals 2/3. So for the circle, we have r equals 3/2 centered at the origin, means that that is the formula for the circle. And so this would be g of theta. So the area would be the integral from negative 2 pi over 3 to 2 pi over 3. We do not have to break this up. Of the area of the circle, the outer region, g of theta, quantity squared, minus the area of the inner region, the cardioid. And we can combine these two integrals to just be one integral. So we can pull out the 1/2, and we get 1/2 integral from negative 2 pi over 3 to 2 pi over 3 of g of theta squared. G of theta was r over 2, so that's 9/4, minus f of theta squared, which is 1 minus cosine theta quantity squared, d theta. This is 1/2 integral from negative 2 pi over 3 to 2 pi over 3 of 9/4 minus 1 minus 2 cosine theta plus cosine squared theta. Go ahead and distribute the square, which is 1/2 integral from negative 2 pi over 3 to 2 pi over 3 of, distribute the negative sign, 9/4 minus 1 is 5/4. Distribute the negative sign to plus 2 cosine theta, and then minus cosine squared theta. We can integrate 5/4 and 2 cosine theta. To integrate cosine squared, we have to do the half angle formula again. So that's 1/2 integral from negative 2 pi over 3 to 2 pi over 3 of 5/4 plus 2 cosine theta minus 1 plus cosine 2 theta over 2. Which, last manipulation before we actually integrate this, this is 1/2 integral from negative 2 pi over 3 to 2 pi over 3 of, we have 5/4 minus 1/2, which is minus 2/4, so that is 3/4, plus 2 cosine theta minus cosine of 2 theta over 2 d theta. We now integrate this. This is 1/2 times 3 over 4 theta plus 2 sine theta minus sine of 2 theta divided by 4, evaluated from negative 2 pi over 3 to 2 pi over 3. Almost done. This is 1/2 times, evaluate this at 2 pi over 3 and negative 2 pi over 3. Let's do this in one step. 2 sine theta of 2 pi over 3. We'll break it up into one step. Never mind. So this is evaluating at 2 pi over 3. And then minus 3/4 times negative 2 pi over 3. Minus 2 sine of negative 2 pi over 3. Plus sine of negative 4 pi over 3 over 4. Okay, start to cancel. 3/4 times 2 pi over 3. The 3's cancel. The 1/2, the 2 and the 1/4 will turn into 1/2. So we get pi over 2. Coming over to this value, we have negative, the same thing. So we'll be adding another pi over 2. So blue means we've already taken care of it. I think I dropped my 2 right there. Sine of 2 pi over 3 is root 3 over 2. And negative 2 sine of negative 2 pi over 3. Sine of negative 2 pi over 3 will be negative root 3 over 2. The two negatives will cancel, giving us another 2 root 3 over 2. Sine of 4 pi over 3 is minus 1/4 is going to be a negative root 3 over 2. And then we have plus the last one, we have the 1/4. Sine of negative 4 pi over 3 is going to be positive root 3 over 2. Okay, this is 1/2 times pi over 2 plus pi over 2 is pi. The 2 and the 1/2 cancel, 2 and the 1/2 cancel, giving us plus 2 root 3. We then have plus root 3 over 8, plus root 3 over 8 is plus root 3 over 4. Distribute the 1/2. This is pi over 2 plus root 3 plus root 3 over 8, which is pi over 2 plus 9 root 3 over 8. So that area that we started 45 minutes ago is pi over 2 plus 9 root 3 over 8. Now, I know this is ugly, because I mean, look how long this was. This was a lot of steps. But it was still easier than doing Cartesian coordinates. Doing those 3 integrals would be hard. Finding the equation for this cardioid would be hard, and who knows if we could even integrate that. Okay, last definition of the course, or theorem, or formula. We have the arc length of polar coordinates. The arc length of r equals f of theta from theta equals a to theta equals b is L equals the integral from a to b of the square root of r squared plus dr d theta quantity squared d theta. So an example of this find the arc length of the cardioid r equals 1 minus cosine theta. Same cardioid as the last example, but we're finding the arc length. Solution, we're going to need r squared plus dr d theta quantity squared. So let's go ahead and manipulate this and get it as reduced as we can before plugging it into the integral. So r squared is 1 minus cosine theta quantity squared plus the derivative of r with respect to theta is sine theta quantity squared. Go ahead and square the first term. We get 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. We have cosine squared plus sine squared, that is 1. So r squared plus dr d theta squared is 2 minus 2 cosine theta. Thus, the arc length of the cardioid, we're only going around the cardioid once, so that is from 0 to 2 pi, is the square root of r squared plus dr d theta squared, which is 2 minus 2 cosine theta d theta. Okay, we can pull the 2 out. This is the integral from 0 to 2 pi of the square root of 2 times 1 minus cosine theta d theta. Well, this is the integral from 0 to 2 pi of, if we multiply under the square root by 2 over 2, that would be 4 times 1 minus cosine theta over 2 d theta. The square root of 4 can come out as 2 times the integral from 0 to 2 pi. And then 1 minus cosine theta over 2 is exactly sine squared of theta over 2. So this is 2 times the integral from 0 to 2 pi of sine of theta over 2 d theta, which is, we have 2 from outside the integral. The integral of sine is negative cosine, so we're going to get a negative cosine of theta over 2. But when doing your substitution u equals theta over 2, the d theta is going to equal dx, 2 dx, which gives us another 2 in front of the cosine. Evaluated from 0 to 2 pi. So this is negative 4 times cosine of pi minus cosine of 0, which is negative 4 times negative 1 minus 1, which is 8. So the arc length of your standard cardioid